Well, when I left off with part 2, I wasn't sure if I was going to do a video for part 3, but I have decided to go ahead and do that. And part of the reason is that, well, I made a few mistakes in part 2, or at least I omitted some things I should have covered. And I thought of some things and also discovered something very interesting. So let's try to move on and do some more measurements on this Zenith AM shortwave radio from 1938. As you recall from parts 1 and 2, what I've been doing is using a signature analyzer to see if it can improve the troubleshooting procedures in an old radio of this sort. And by troubleshooting, I mean the kinds of tests that you might do before you even turn the radio on, to find bad resistors, bad capacitors, things of that sort. Now, I don't propose to do any tube testing on this particular radio, though tube testing is also probably a good idea before you try to turn anything on, to make sure you don't have any shorted tubes especially. Okay, so what are some of the things I forgot in part 2? Well, one is when I was explaining some of the circuitry, I forgot to mention, and I'm sure a lot of you have noticed this already, that there is a capacitor between pin 3 and pin 4. And so even when this transformer is out of the circuit, in other words, when I've pulled the plug on this, there's still a capacitor from there that leads down and eventually goes to the B plus line. And by the way, also, I called this common in part 2, and maybe I should have just called that B plus, but anyway, it's the common power line for all of the stages. The second thing is I didn't do any measurements with the transformer and the field coil plugged in. So I went ahead and did some of those, and I'll show you those in a minute. And then finally, I moved on to the RF and IF stages, the 6A8 here and the 6K7 here, and did some of the same things. In other words, I measured resistance and capacitance. Initially, I was just going to do all that to ground. Then I wound up doing it back to the common or the B plus, as I did in part 2 with the 6Q7 and the 6K6 that you may remember from that video. So first, let me show you some of the things that I found when I plugged in the field coil and the transformer, and then we'll look at some of the interesting things that I discovered when I started doing signature analysis in the RF and IF sections. Here is the chart that I had in part 2, and what I have done is for the places where it made a significant difference, I have inserted the new values of resistance that I measured after I plugged in the field coil and the transformer, the output transformer. The main differences were in the capacitance readings, though I did get some of the measurements did change with respect to the resistance, but I'm not going to really go into those. I mainly noticed that on the plate, the measured capacitance with the meter went from 5 microfarad to 19 microfarad. And so you may wonder, well, why is that happening? Well, what is now happening is that the field coil is forming a partially resonant circuit at 60 cycles with the two capacitors that are in there. Now, the capacitors are about 9 microfarads each, but once you connect the field coil, they are essentially in parallel. And so you read almost 20 microfarads across the two. The couple of other things that I noticed, well, and noticed that the screen grid also doubled to 20 microfarad for the same reason, because of course the field coil actually shunts the two positive leads of the capacitors together, so that instead of isolated 10 mic capacitors, or actually they're 8s that read 9, the capacitance that the circuit sees is 20 microfarads. But an even more interesting thing is that the signatures changed. Instead of just a straight line, now I get a flat ellipse on the plate of the 6K6. I get an actual angled ellipse instead of an almost flat ellipse. Notice that before it was between E flat and E angled, and now it's very definitely a 45-degree E angled. Same is true of the cathode, where I used to get a straight line but at an angle indicating a resistance. Now, because of the added capacity that the field coil puts in, I get an angled ellipse. Similarly, over on the with respect to B+, I got similar things that I didn't write down here, but basically inserting the field coil and the output transformer did make a significant difference in the signatures. It also made a significant difference in the capacitances, at least with regard to the plate and screen, which are the pin electrodes that connect directly to B+, or almost directly. On the 6Q7, I didn't notice a great deal of difference with the transformer plugged in, and you wouldn't expect that because this circuit remains pretty much the same with or without the field coil or the output transformer. So, some interesting things on the signatures, but let me now shift to what the real purpose of this part 3 was going to be, which is looking at the RF stages. Here are the RF stages of the, or I say RF, the radio frequency stages, in other words, the RF and IF stages of this Zenith radio. The converter is a 6A8, and these are often called pentagrid converters because they have 5 grids. If you're not familiar with this, you might want to go back and look at some of my earlier videos on how tubes work. I talk about the pentagrid converter a bit there. The 6K7 is a normal pentode that is used for the IF, and of course the way that the system works is the signal from the antenna is coupled through the antenna coil, applied to the converter. The converter mixes the antenna signal with a locally generated oscillator signal, and this tube actually serves both these purposes. In other words, it's sometimes called an oscillator mixer. Many people just call it a converter. At any rate, it mixes the two to produce an intermediate frequency, which is tuned by this transformer, passed through this intermediate amplifier, and to another tuned circuit that then couples it over to the detector, which is inside the 6Q7. So I looked at particularly the active elements of the 6A8 and the 6K7 with regard to resistance, capacitance, and signature. So let's take a look at the readings I got. Here is the section on the 6A8. And the pins that I probed are 3, 4, 5, 6, and the top cap. Now understand the top cap is disconnected from the tube, so this is the top cap reading back into the chassis. That's the plate. The pin 4 is grids 3 and 5. Pin 5 is grid 1, pin 6 is grid 2, and the top cap is grid 4. So what did I see? Well, 2.2 meg here, 19 meg there, and so on. Remember, this is with regard to ground. And if you remember the schematic, there's no direct path from these, no DC path directly from here. This is an unusual radio in that it does not use the chassis as B minus. So you would not expect to see any DC path to ground, although there is some, what you might call sneak currents, that do find its way through a variety of components to ground, but it's pretty high values. So 1.8 meg, 16 meg, 17 meg, and 2.2 meg. The only one that's relatively low is the 0.3 ohm reading on G1, and we'll look at that in the schematic in a second. Then we get these readings for capacitance: 10 microfarad, 2 microfarad, 0.4 nanofarad, 4.6 microfarad, and 0.2 nanofarad. Then I'll come back and talk about the signatures in a minute, but notice that when you reference to the B+, now you do get direct paths, DC paths: 25 ohms, 2.5K, 4.7 meg on pin 5, which, remember, that is only 0.3 ohms to ground, that is to the chassis, but it reads 4.7 meg back to B+, 18K on grid 2, and 7.5 meg on grid 4. With regard to capacity, you see what I get there, and the only thing that is of much note is on G1 you get 9 microfarads. I think that's what I wrote down there. And that is basically the power supply capacitor that you're reading. On the 6K7, the pins 3 and 4 are read open in terms of, in other words, infinite resistance. Here are the capacity values. Once again, the plate, because it feeds back to the B+, is actually just reading the capacity of the power supply. Like I said, I talk about these signatures in a minute. And then, similarly, the plate of this tube, 32 ohms, or I'm sorry, 32 ohms versus 25 ohms, that just reflects the DC path back to the power supply. And then 25K, you notice on the G2 of this tube is very close to the 25K on G3 and 5 of the pentagrid converter, which is basically the screen grid of the pentagrid converter. Once again, same thing with regard to capacitance readings. So no big surprises here, though I am going to compare these resistance readings against what I think I see in the schematic to see if maybe there are some other resistors that may have gone up in value over the years. But now let's talk about the signatures that I read. Let me move this over just a little bit so we can see this right-hand column a little better. So the first set of numbers or of legends are the signatures that I got on those pins, in this case with respect to chassis, in this case over here with respect to the B+. But that was at the default frequency, which is, I think, 10K, 10 kilocycles. I then ran the signature analyzer up to 100 kilocycles or kilohertz, and I got a different pattern. In other words, this was an angled ellipse. This is a flat ellipse. This was a flat ellipse. This is an upright ellipse, in other words, straight up and down. Here I only got an up and down line, but when I ran the frequency up to 100 kilohertz, I got an upward ellipse. Similarly here, I got a flat line, but with the 100 kilohertz, I got a flat ellipse. Now on G4, I got the same thing, no matter what the frequency. Similarly down here, I got different things, and I won't go into all of those, because what I want to show you now is what happens to signals. And I think what I'm going to do is use, for example, Well, let's use the plate of the 6A8 as an example. What I'm doing is the probe of the signature analyzer is on pin 3. And once again, this is the 6A8, this is the 6K7. In other words, this is the converter tube. This is the IF amplifier tube. And you notice I have the plate caps disconnected. That's partly just because the additional height makes these wires too short to connect it. But I have the signature analyzer connected to pin 3 of the 6A8. So now let's go over and take a look at the signature that we see on the software. So the signature you see on the screen is the default signature. That is, when I click on capacitor here, it sets a default amplitude and a default frequency. And you see that I would call this an angled ellipse. But now, watch what happens as I lower the frequency. You notice that at a frequency around, let's see, that's around 53.9, 54 hertz. Let's go a little higher. You see that the ellipse actually opens out. In other words, below that frequency, it tends to be a little flatter, and above that frequency, it tends to be a little flatter. Now, we'll go on up to the 10 kilohertz where we were. By the way, this is about 1 kilohertz. Then we go up to 10 kilohertz. And now let's go on up to 100 kilohertz, but we'll do it slowly. Watch what happens to the ellipse at one frequency right there, which is around 16.7 kilohertz. It becomes almost a straight line or an angled line. In other words, it looks like a resistance, a pure resistance, pretty much at that frequency. Then as we go up, it opens up, then it flattens out as we get up to 100 kilohertz. Now, what I find interesting is that there appears to almost be a resonance around this point, which is around 27, a little over 27 kilohertz. Now, remember, that's the plate of the converter tube. I found similar behavior in many of the other areas in and around the RF sections. In other words, around the converter tube and the IF amplifier tube. So let me move the probe and show you another kind of interesting signature. This is the plate of the IF amplifier, in other words the 6K7, at 60 hertz. Now I'm going to slowly raise the frequency, and I'll call out a few values in the middle so that you'll know about where we are. That's 60. That's about 1 kilohertz. Now we're up to about 8 kilohertz, 10 kilohertz, 20 kilohertz or so, 30 kilohertz, 40, 50. Now watch what happens to the ellipse though. Now it becomes a straight up ellipse. In other words, it went from a flat ellipse indicating a relatively open circuit. In other words, a capacitor with very little resistance in parallel. But as the frequency goes up, it actually becomes almost a perfect circle at around 36 kilohertz. And then as you go up further, you notice it starts to look as though that it's a relatively low resistance in parallel with a capacitor. Now I want to think about this some more, and perhaps some of you might want to put some comments on what we're seeing here. But I want to compare this to the schematic, and if something interesting occurs to me, I'll add that to the end of the video. But otherwise, I would like to say that I was hoping that I would get some interesting results in the RF sections, particularly because I'd like to use signature analysis to see whether, for example, you can determine if the IF transformers in a radio of this era, around 455 kilohertz, if you can determine whether they will resonate at or around the IF frequency. In other words, whether the radio will tune its IF frequency correctly. Now, the last thing I'm going to do is I'm going to leave this at 100 kilohertz, but I'm going to move to pin 3 of the let me make sure that I'm on the right pin. Yes, pin 3 of the 6A8. That is the converter tube. And now I'm going to tune the receiver. Well, it looks like it has little, if any, impact on that. So what I'm going to do is go over to the, well, let's go to pin 4. And now we'll tune the receiver. No difference. I think I'm going to do the band switching. Okay, let me go to pin 5. Tuning doesn't appear to have any impact on that. Let me now switch the bands. Okay, there is a difference. Notice that the angle changes slightly as I change bands. So let me now retune. Oh, there, it does make a difference. It does show, I think that's probably the shortwave band. It looks like I might have a dirty capacitor there, dirty tuning capacitor. Yeah, it looks like, or maybe it's just the ground. I have some kind of intermittent going on there. So I'll want to look at that. But I think what I'm going to do at this point is kind of end this, because I'll probably carry on and do some more experiments, and maybe at some point in the future I'll come back to this with some future videos. But for right now, I think this is enough to show you that signature analyzer can probably be of some use. But don't forget some of the simpler things, like just simply measuring the resistance to ground or the resistance to the power supply or the capacitance of various areas. With a modern multimeter, you can do a lot of tests in an old radio without even turning the power on. So if there's any message here, it is find a schematic that matches your receiver, do some resistance and capacitance measurements. If you have a signature analyzer or you have the components to build one, go ahead and do that and try that. But basically, compare what you read with what you see on the schematic and see if you can find out where there might be components that need to be replaced, or at least further checked, even before you turn the power on to one of these older receivers. So I hope this has been interesting. I thank you for watching. I hope you'll look forward to some future videos, although I think at this point what I'm going to do is shift gears a little bit. I usually do after I've done 2 or 3 on a particular subject. So look for something different next time. And in the meantime, have a nice day.